5 minutes talk and another 5 minutes for questions.
Thank you very much.
Okay, please go ahead.
Let me start by thanking Professor Narita for organizing this meeting. It promises to be very interesting and very beneficial, and we really appreciate all that you and your team have done. Thank you very much.
Thank you.
I am delighted to have the opportunity to tell you most of what's going on in the U.S. in our field. And I'll start in kind of a strange way by telling you what you already know. I have trouble staying near the microphone, so yell at me if I leave. So our field has two branches, science and business. Science, of course, striving to understand how is it possible to produce nuclear reactions at low energies, low temperatures. And of course, there's the normal combination of theory and experiment to address that. On the business side, we're several people in the room, myself included, are seeking to make a yen or a euro or a dollar on this field, not solely for selfish reasons, but because this field has the opportunity to do real good for humankind. So we're motivated by a couple of things, and to commercialize LENR, you need two things. You need machines into which you put materials and reactants, and out of which you get heat, okay? So both those sides are being vigorously worked by people in this room. Now let's see if I can do this. Okay, so that serves as an outline for my presentation. I'll go through those 4 topics that are indicated in yellow there. I'll talk a little about the past, mostly about the present, and at the end we'll present a concept on a materials program which is new, not yet funded, and I think is very important, and I hope that generates some discussion. Also be talking about various organizations and programs, and I will start out with that. Okay, so here is a summary, hopefully complete summary, of the organizations involved in LENR, private and public funding sources, and then information sources on the bottom. We're fortunate for the science side. We have the International Society for Condensed Matter Nuclear Science, ably led by Alan Smith and Lynn Bowen. And then Steve Katinsky and I formed the Industrial Association about 15 years ago in anticipation of the development of an LENR industry. Private funding, the box on the left is dotted because that's past a number of people who did fund the field. And currently we're fortunate to have the funding from Industrial Heat and from the Anthropocene Institute, as well as the other sponsors that you just saw listed on the graph that Professor Narita showed. Major programs, the DASH program, Google, is completed. The other programs are still in operation. We'll hear about the ones in the US, the ARPA-E program from me, and about the others from the following speakers. And I'll come back to the information sources at the end of the presentation. So addressing theory in the United States turns out to be quite challenging, because at one time there were many people doing a lot of different theoretical approaches, okay? And now it's boiled down to 3 main people. Mark Davidson, who published a serious paper roughly 10 years ago, is still interested but not active. Andrew Muhlenberg has published many papers, 19 of them lead author. And then, of course, we're fortunate that Peter Hagelstein has been active since the beginning of the field with a very large number of papers. And he'll present a paper, I think it's tomorrow, I should have checked that, at this conference on his latest work, Progress on a Model for Anomalies in Condensed Matter Nuclear Science. So I feel apologetic showing so little about theory in the US, but there really isn't a lot going on right now. It's mainly experimental work, and I'll get to that in a moment. So the private funding, I say the few individuals who, not all of whom wanted to be known, and I'm aware of who they are, but they don't want to be listed. Then we have the Industrial Heat. Dewey Weaver is here, there he is, happy that he is here. And then we have a serious support from Carl Page. Is Frank Ling here yet? I haven't seen him. There he is in the back. And the other people from Anthropocene. So this is critical funding. It is on a level different than the government and major industrial programs, but it's very, very important. I expect that most of you know about the Google program that ran for 4 years, $10 million roughly total. And the reason I'm including it is because it raised the bar for research in this country, and I have been told that the paper they published in Nature was instrumental in getting the European program started. I haven't had verification on that, but I believe that's true. And the reason I'm including this is partly for the links that are on the bottom there, so you can find out the many very solid papers that were published by Matt Trevithick and his colleagues in that program. Okay, so let's get more up to date. I'm giving a review on work in the US. Florian Metzler, about a year ago, gave a similar paper, and the link to the YouTube video on that is there. I'd recommend that to your watching. So we have an ARPA-E program announced in January a couple of years ago, started roughly a year ago, and some of you may be sitting there expecting me to give you results. Sorry to say, they really haven't published anything yet. There's nothing available by way of results from that program. Okay, but I should tell you about it. So what I will do is walk through those contractors, 1, 2, 3, 4, 5, 6 main contractors, and the 2 at the bottom are doing supporting work. So the following view graphs are going to give you information about the work statements in each one of those programs and the funding. That's the good news. The bad news is words, too many words. Okay, so if you stay with me, I can give you a feeling for that. Now, the interesting thing about this program, before I get into the individual projects, is that it is the flip side of common interest in LENR. Many of us are here because of the excess heat, the practical promise of making new clean energy sources. But there's also transportation data, and there's also fast particle data. So the interest declines rapidly when you go away from the excess heat, because I've never heard a scheme to make money on the transportation results or on the charged particles. Okay, but this program is the inverse. They don't give a hoot about calorimetry. They're a little interested in transmutations, but they're dominantly interested in charged particles, which is the weakest source of information about LENR experiments. And the reason is they're aimed at convincing physicists of the reality of LENR, where most of us who have looked at the literature, written a large part of the literature, are convinced of the reality. Okay, so this US program is good but not great. Good in that it includes a lot of good people doing good experiments, but not great because it does virtually nothing for the theoretical side or for the commercial side of our field. Okay, it's aimed at physicists. So I'll show you a few view graphs on each of these programs. This first one is done by Energetics Technology, a company on the East Coast. The Naval Research Laboratory is a subcontractor. And the sketch at the bottom is what resulted from David Kidwell at the Naval Research Lab telling me what he's doing. So it's a 2-part experiment, an electrochemical cell from which you can do co-deposition of palladium and deuterium onto a thin metal layer that both serves as the cathode in the cell and a light barrier for a scintillator photomultiplier. So the fundamental scheme here is if particles are emitted from the co-deposited palladium deuterium material, then you have a large solid angle, almost 2 pi out of 4 pi, in order to intercept the particles and record them in the multiplier. Okay, so that's a well-designed experiment in good hands, which should lead to good results, but there's nothing available yet. The next 2 programs, MIT and Stanford, are on one hand laser stimulated, on the other hand phonon stimulated. The first one involves gas-loaded metal hydrogen systems. The next one, nanoparticles, again with gas loading. So there's a mix of different loading techniques and different measurements here. The measurements, as I say, skewed towards particle measurements. So these graphics will be available. If you want to look at details, you can do that, but I don't think it's worthwhile taking time going into a lot of detail here. Now, there are 2 programs, the University of Michigan and a company, Amphonic, aimed at nanocomposites. And they're basically traceable to the very good work that's been done in Japan on nanomaterials and now in Europe with the hydrotelexites, John Paul's work and others. So this is a pair of papers, a pair of programs that are focused on nanomaterials and particle measurements. The Lawrence Berkeley lab, Tom Schenkel and his colleagues are in this program as they were in the Google program. This is a photograph from their setup in the Google program. They too have a two-part experiment. The upper part is a electrochemical cell in which they load a palladium foil, and then from the bottom with the vacuum system, they shoot particles of deuterons at low energies in order to look for enhanced cross-sections, very much like the work of Kasagi and Chursky and their colleagues, and others too. So that's the experiment in Berkeley. Now the two supporting projects are being done by Texas Tech and the University of Michigan, and they basically are, the first is oriented towards materials and also detecting nuclear products, but mainly materials, and the second one is a detector experiment. Okay, mainly if you're in the program and you want to improve your nuclear detection capabilities, you go to these people. So I would expect that the few view graphs that I just showed you on the ARPA-E program will not be the highlight of your week. But you can come away with a feeling that there is a program, a significantly funded program by ARPA-E, the Advanced Research Project Agency for Energy, that is grinding away, and we can expect results on a scale of a year or so. So other U.S. labs doing LENR experiments, of course, Mitchell Schwartz has been at this for a long time, done a remarkable series of instrumentation development and measurements. Fran Tanzella, where are you, Fran? Here's Fran, is doing experiments in his Energy Research Center. And then Tom Clater is also doing things. Here at the LEC table, we have Frank Gordon and Harper Whitehouse. We'll be talking about the lattice energy converter during this conference. And finally, we have work done at the NASA Glenn Center by Bennu, Forsley, and others. The two Dennises are working for industrial heat, Dennis Letts and Dennis Cravens in their labs. And then at our university, three of us, MM, as well as Emma Morano. Where's Morano? There he is. Okay. I have the good fortune of him working with me for this year. And we're doing electrochemical experiments and some ancillary experiments on co-deposition and electromigration. So that is a summary. Now, some of you say, where's Ed Storms? I thought I heard, where's Ed Storms? Okay, so Ed and his wife had to move recently from the home and abandon his lab, but fortunately he's still involved in the field, and we'll hear from him later in this conference, but he's no longer a lab animal. Okay, so switching from the research side to the commercialization side, this is my attempt. I just learned there's of another company that should be on the list here. But anyway, these are the companies I knew of when I prepared this talk. The ones surrounded by orange are not in the U.S. The two at the bottom are in the U.S. And I'll show a single view graph on each one of those, Rowan and Leonardo. So this is a diagram. It's not very new, but it shows that the Rowan people are working towards a reactor, including what they call a hot tube. It's distinguished by having hydrogen input and output, and also very short pulses. They call them Q pulses that excite rod-shaped materials that are plasma sprayed. And if you want to know more about that, Fran Tanzella can tell you a lot because he works closely with them. Now, Leonardo is a problem because Rossi has a complex history, to put it mildly, in both Italy and the US. And on top of that, his recent pronouncements are that this isn't a nuclear reaction that he's working with. Rather, it is exploitation of zero-point energy. So I will say no more other than to tell you that if you want to look into what Rossi's doing, there are ample links to the activities in the ECAT world. I'll leave it go at that. Now, I'm going to do something which is debatable. You want to know what, I assume, I was asked to talk about what's going on in the US, but we're planning something that I think should be important, and I would like to tell you about it now for a selfish reason. I'm hoping that I will get some good feedback from you, that, you know, oh, hey, Nagel, that program looks looks nuts, or, do this instead of this, or whatever. Now, we need two things in our field: generators and materials to put into the generators. We talked about that. The development of generators is going on in the companies that are listed and in other places, but there is less work going on in materials development, okay? Now, from my perspective, that needs work. There should be a dedicated program, in my view, in our view, to develop materials for LENR, which will do two things: perform at high levels and last long enough, okay? You buy an LENR generator and you have it installed in your home, high power density, local generators. And you say, gee, it feels very good in here. We have heat, we have electricity. And 3 days later, the materials don't work anymore. They got to work 3 months, 6 months, a year, a long time. Okay, so that is our argument for wanting to have a focused materials program, and that will enable the production of LENR and produce desirable characteristics, good energy gains, and so forth. So we have to produce and maintain effective materials. And from my perspective, this is very much like the early days of the semiconductor industry. They knew silicon was good, but silicon had impurities in it. And it took a long time to get to a point where you could bake silicon in large volumes, cut wafers, and produce chips and so forth. And I feel as though we are in a similar situation in our field, having to master the materials thing. Now, this is another overly wordy view graph, but the bar was set very high by Vittorio Violanti and his colleagues when they had a program on materials development, materials testing, and they got a lot of very, very good results. So in red, you see they modified materials, studied them with good methods: scanning electron microscopy, atomic force microscopy, energy dispersive chemical analysis, performed calorimetry experiments on the known materials, the well-studied materials, and then could feed back. And they found certain things work better than other things, like a 100 crystal orientation. I won't go through all of these. They published papers, you see, 2008 and then later in 2015. So we look on that as a model of how things ought to be done: a sustained, systematic program with adequate instrumentation and good people in order to solve the problem. High performance for adequately long times. Okay, that's what we're looking. So if you're a materials person, as is Imam and Morano and myself, you say you have certain things to do. You form the materials, treat the surfaces, study the load, and get results. There's a possibility of a feedback loop indicated in the bottom here. So what we're talking about is buying and making and modifying and characterizing materials and then testing them for their LENR efficacy. So the production of LENR materials, we need, in this field, we need two things: mixing and motions, M&Ms, okay? The mixing has to do with putting hydrogen isotopes first onto and then into materials. And the motions are prerequisite to the interactions that are prerequisite to reactions. Okay, so we have the three main techniques: loading, started with Fleischmann and Pons; co-deposition from Spock and his colleagues in San Diego; and then some dry mixing experiments that Mitchell Schwartz has done. And we think all of those are worth examination. The testing has to be done. We have to do, as Violanti and his colleagues did, to find out what works. Okay, this is possible. I look on the semiconductor industry as the model. So we have three methods of loading and excitation have been found to produce LENR: electrochemical cells, hot gases, and plasmas. So what we're contemplating is the development of materials and then the testing of them by all three of the methods. And you see down at the bottom here, there's been a question in our field for a long time: what if something works in an electrochemical cell? Will it work in a glow discharge? Will it work in a hot gas experiment? How well, how long, and so forth. Okay, so we're advocating for a materials program, and it will include testing by all three of those methods. So three methods of loading, three methods of preparation: loading and co-deposition and dry mixing, and then three methods of measurements. This is the organization diagram for such a program. We know two things: who to hire and what to do. Okay. Now I have a spreadsheet that lays out the costs of this program. Okay, I'm not going to show it's too much details, but it's another $10 million program, $2 million up front for equipment, and then 4 years at $2 million a year in order to pay the salaries and the requirements of these people. So I am going to vigorously try to sell this program after this conference, and I'm hoping, to get comments back from you on any or all parts of it. I would very much appreciate the feedback. Now, the last couple of view graphs have to do with our colleagues developing hot fusion. And this is a screenshot from a TV program in the US a couple of years ago. So these are the companies that are known to be working on hot fusion. There have probably been some others added since then. And some of them are rather well-funded, in the ballpark of $1 billion for a given company. Now, I'd like you to think about some numbers for a moment. In fact, I'd like to do a quiz. The question is, what is the annual turnover for energy globally? Okay, the answer is 10 trillion, roughly. $10 trillion goes into energy globally. Okay, so these hot fusion companies have tens of billions of dollars. We have tens of millions of dollars. Okay, so we're funded at the rate of about one part in 1,000 of the hot fusion companies, and hey, I want them to succeed. We need a variety of energy sources, of course. Big central power stations are okay. We're working towards something in your home, and I'll make that point by showing this view graph. The diagram on the left you recognize as ITER, a International Thermonuclear Experimental Reactor in the south of France. If you look on the left there, 1, 2, 3, 4, 5 floors, so that's like 50 feet, more than 15 meters. And what we're striving to do is develop a nuclear power source on the scale of a desk. Okay? Because we have high power density, condensed matter. The reactants are close to each other, not dilute plasma the size of a bus. Okay? So I view this, I view it as a competition, frankly, between our field and the hot fusion field. Okay? But it's not that I want them to fail. I say I want them to succeed. But we have something that we can sell that they can't sell. Almost all of their prospective systems, based on the experiments that they're doing now, are large, are going to be central power plants. Okay? So that's just the reality of the situation. And I would like you to remember this from this conference, that we have something that they don't, that is the potential for very small generators. So I hope it hasn't been too fast, but I am down to my last graphic. I can leave this up while I try and answer any questions or complaints or arguments or whatever's on your mind now. So thanks for your attention. Thank you again.
Okay. Thanks, Dave. So any questions or comments to Dave? If you have, please come to the microphone, please. Yeah. Okay.
Hi. You mentioned testing many different materials under different triggering conditions.
Hello? Yeah, there we go. It's common in the battery industry to do combinatorial experimentation. And we were talking earlier about how that might be easier than developing theories, et cetera, but I haven't seen any companies that approach LENR with the combinatorial approach. I proposed it at MIT about 10 years ago, using certain soft ionization detectors and things like that. Is there anybody you're familiar with that works in that area?
I appreciate your comment. It's important. There was, at the NASA Center in Virginia, they had a program with combinatorial approach where they made, where where they varied two parameters. I don't remember what they were, but they had a substrate like that with dots on it in two directions.
Oh, yeah.
And then they looked for evidence of LENR when they put it in a gas chamber. So that program didn't go anywhere, okay? But it's a technique that should be used. And I expect that combinatorial experiments will be done in the materials development program if we get funded to do that. Okay, appreciate the comment.
Yeah.
Thank you.
Yeah, it's common in the biotechnology world, you know, it's, there's a lot of high throughput equipment that could be repurposed, so it's an area of interest. Thank you.
Yeah, and if you deposit materials, thin films, onto a substrate, and you can, you know, look at the results with infrared cameras, as well as many other temperature sensors. So I think the approach is important, and I appreciate your comment. Thank you.
Thank you.
Grenier.
Thank you, David. With regard to your commentary about long-term tests, there's very long-term systematic studies being conducted by Binja and Huang's group in an area which you didn't mention, which was cavitation, which I think is a very important field of study, which has proven observation of transmutation. But I have one other, given your special executive service access rights, do you know what happened to the Proton 21 lab that came out of Kiev, was tested in Chicago, Illinois between 2015 and 2017, and then sent to Brookhaven National Laboratory? Are you, and because that was the largest systematic study ever done in transmutation.
Yeah, I don't have anything to say about that. It's not because I know something and can't say it. I don't know anything. I'm sorry to say. Now, Vysotsky is here. I don't know if he has.
He worked with them, didn't he?
Yeah, so maybe you can. Here's Vladimir over here. If
Vladimir, do you know what happened to Vladimir to SV Ademenko's lab? Do you know what happened to SV Ademenko's lab? What happened to it? Okay, no answers. Thank you very much.
So I'm totally ignorant. He's not ignorant, but he's got other restrictions. But thanks, Bob.
Okay, so any other questions, comments you have? Yeah.
Hi, David. Siddharth here from LENR. Have you seen hydrogen being a consumable? Does it last the fusion?
Are you asking if LENR experiments with hydrogen rather than deuterium work? Is that what you're asking?
Was the fuel being consumed during the time of reaction?
Yeah, I think the evidence is yes. Now, we're the folks from Buwan. They ought to be able to answer that quantitatively.
Yeah, trust me, it's very difficult to measure those very small amounts. And I don't know anybody who's done it successfully.
So we've got around 4.2 milligrams of hydrogen. We're not using deuterium. And my reactors have been running for 3.5 years. And if I even take 5% as the rate of fusion, they shouldn't last more than 4 to 4.5 months. We're talking about 10 to the power, say, 13 molecules of hydrogen, but it's defying all the logic. I'm just shouting at a theory. Is there another reaction after helium-3 and helium-4? Something else is happening.
Yeah, so I can't respond to that. Do you have a comment? There's somebody. Do you have a comment? Oh. Okay, he's going to talk after. So anyway, you raised a question about hydrogen consumption. I don't know if anybody in the room can comment on it. I would appreciate the comments if they could. There's been work on deuterium consumption. Mitchell Schwartz did some, but I don't remember the numbers. Okay. So thanks for raising the question.
I think that might be the holy grail of LENR and how we cross the coal line to get to hot fusion, coming down to cold fusion.
Yeah, that being hydrogen reactions or additional reactions beyond.
After the fusion, yes.
Okay, good. Thank you.
If I may, on this question, I had the same question for a long time. Recently, I've been talking to researchers where they have excess hydrogen production in such a reaction. So it might be that you consume some, but you produce some. I don't know.
I just have a theory out here. So when I look at the amount of energy coming out of every fusion versus there is an energy being consumed for splitting, so which means it's a closed loop and you are actually replenishing your fuel. So that explains 3.5 years of running and still the reactor not diminishing in its performance. So that's a theory. I don't know if we can talk about it. I think we have a very big eureka moment there.
Yeah, I learned something. So Fran, you're saying that Berwan has not been able to do an accounting on the hydrogen, even though it's a closed system?
No, the system is not.
Okay.
But like I said, I don't know anybody else who even has a weak system who has the capability of measuring those small quantities.
Okay, good. So thanks for your attention. Very much
Okay.
appreciate it.
So, okay, let's thank that.